Hello everyone. Today we are going to discuss about the full wave rectifier. In the previous class, we discussed about the what is half wave rectifier, what are the parameters in the half wave rectifier that we discussed in the last class. Okay, this is also same as half wave rectifier only, but here we will get the two cycles are generated at the output in the full wave rectifier. Okay, there are some disadvantages in the half wave rectifier. To rectify that problems, now we will see whether this full wave rectifier is having the full efficient or not, that we will see here. So first we'll see so what is full wave rectifier? In full wave rectifier, both positive off cycle and the negative off cycles are processing to the output. Both the positive and negative are processing to the output here. That is, two cycles are generated at the output of the DC rectifier. Okay, now if we see the waveform here, this is assume that it is a voltage waveform. Okay, this is with respect to omega t. Okay, this AC we are giving to the full wave rectifier circuit, whether it is maybe center tapped full wave rectifier or bridge full wave rectifier, because we have the two full wave rectifiers, center tapped full wave rectifier and the bridge full wave rectifier. If we give the AC supply to the full wave rectifier circuit, we will get the pulsating DC like this. Two cycles are generated here. Both the positive off cycle and negative off cycles are processing to the output. So this is also assume voltage waveform and with respect to omega t. If you give the AC supply to the full wave rectifier, the two cycles are generated at the output. This is called as a full wave rectifier. If you see the center tapped full wave rectifier, so first discuss about the center tapped full wave rectifier, after that bridge rectifier. Center tapped full wave rectifier. This is a center tapped full wave rectifier diagram. So which is having the two diodes. It has two diodes. Assume that it is a diode D1 and it is a diode D2. Okay, now here this is a transformer, and for this transformer we are giving the input is AC. Input is AC, input AC, that is 230 volts. We are giving input AC to the transformer. We are using the step down transformer. This step down transformer is used to decrease the voltage, and this is called as a load resistance. Okay, it is a minus and plus, and is the voltage we will measure across this load resistance here. This transformer is having the three components. Okay, components used in the rectifier circuit. This it is having the first one is a transformer. This transformer is used to step down the voltage, because the DC voltage levels are very small. Okay, that's why we use the step down transformer to decrease the voltage first, after converting into the low voltage, and we will use the diodes here. This is diodes. So what is diode here? Diode, it is used for the switching purpose. The current flows in the diode is a unidirectional current. Okay, which allows the current only in the one direction. Okay, that is a function of the diode here. Now we'll see what is the load resistance. The purpose of the load resistance is used to measure the output parameter at the output end. To measure the output voltage, we are using the load resistance here. So this is about the components used in the rectifier circuit. So we have to write each and every component clearly. What is transformer, what is diode, and what is the load resistance. Now let's see. So there are two cycles here, positive off cycle and the negative off cycle in the sine wave. So first we will apply the positive off cycle to the center tap full wave rectifier. After that we will apply the negative off cycle. Now we'll see what are the responses we will get. For the positive off cycle here, see, it is a positive of the cycle, it is a negative of the cycle. Okay, so assume that it is a voltage waveform. Okay, this for this out of positive and negative off cycle, first initially we are giving the positive off cycle to the transformer, this rectifier circuit. So assume that it is a positive off cycle. We are giving, this is input. Okay, this is AC. Input is AC, that is 230 volts we are giving. Okay, the positive terminal, it is a negative terminal. Okay, this is a positive and negative terminal. As it is a center tapped transformer, okay, we are taking the tapping, load resistance tapping at the center of the transformer here. So that's why it is called as a center tapped transformer. Okay, this is called as a load resistance. Okay, and it is a positive terminal and a negative terminal. Okay, it is VI. Okay, it is also VI here. Input voltage is VI. It is a D1 and it is a D2, two diodes. It is a negative, positive, and the output we will measure across this load resistance. Okay, as we are taking the load resistance at the middle of the transformer, that's why it is called a center tapped full wave rectifier. Okay, now if you see the terminals are which terminal is connected to P type and which terminal is connected to N type of the D1 and D2, we'll see. Based on that, we will decide which diode is in forward bias and which diode is in reverse bias. So if you see the connection here, positive terminal of the input is connected to P type of the diode D1. Positive terminal of the input is connected to P of D1. Okay, now negative terminal is connected to N type here. A negative terminal is connected to N of D1. Okay, this is the one connection here. Next, we'll see one more connection. In the downside, the negative terminal of the input is connected to P type. Negative terminal of the input is connected to P type. And the positive terminal of the input, this positive terminal of the input is connected to N type. Okay, N of D2 here. So this is D2, we have to write clearly. Okay, here P of D2. Okay, it is N of D2. See here, positive terminal is connected to P and negative terminal is connected to N. So we can say directly that D1 is in forward bias. Okay, here negative is connected to P and the positive is connected to N. So here the terminals are reversed. That's why we can say that when the negative is connected to P and the positive is connected to N, the diode will be in the reverse bias condition. Here D1 is forward bias and the D2 is in reverse bias condition. Okay, if you see the practical diode, in the practical diode, when the diode is in forward bias, the total diode is replaced with the cut-in voltage that is connected in series with the forward resistance here. Okay, RF is called as a forward resistance. Now, if you see when the diode is in reverse bias, the total diode will be replaced with the open switch. Okay, now this practical diode, this replacement, we will draw here. So if you take the this practical diode will be replaced with the this diode will be replaced with this circuit, that cut-in voltage practical diode connected in series with the forward resistance here, V gamma, that is connected in series with the forward resistance. Now replace this diode with the cut-in voltage that is connected in series with the forward resistance, as it is a load resistance, negative terminal, and it is a positive terminal, it is a voltage, and it is the open circuited. Okay, as it is reverse bias, we are open circuiting. As a diode D1 is in forward bias, the diode D1 will be replaced with the cut-in voltage connected in series with the forward resistance. As the diode D2 is in reverse bias, the diode D2 will be in the open circuit. Okay, so this is the input voltage and this is the diode D1 and it is the diode D2. Diode D2 is forward bias, diode D2 is in reverse bias. Okay, now we'll calculate. So what is the V0 value we will get if we give the positive off cycle to the rectifier circuit? So this is the positive off cycle we are giving. It is the input is AC input. We are giving the AC supply. Okay, as it is positive off cycle, the terminals are same, positive and negative. Here the positive terminal and it is a negative terminal. It is the input is VA. Here also it is a positive terminal and it is a negative terminal. Here it is VA. Input is VA. So it is V gamma and it is forward resistance is RF and it is called as a load resistance. Okay, so this is called as a load resistance. Okay, it is called as a load resistance. Okay, it is a negative. It is a positive. The output voltage we will measure across this load resistance. As the diode D2 is in reverse bias, we will replace with the open circuit here. Okay, now we'll apply KVL here on loop 1. So I am applying KVL in the above loop. Okay, now what we will get, we'll see. Here the current is coming from, assume that in this I current is flowing, -2 plus VI. So here we have to write apply KVL. Apply KVL. If you apply KVL, see here, minus 2 plus Vi, and plus 2 minus V gamma, okay, is equal to, now we will write the voltage drops here, I into Rf plus I into RL. Okay, from this, if we take the IA separately, we will get Vi minus V gamma divided by Rf plus RL. Okay, assume that it is equation number 1. So voltage, output voltage, V naught, voltage across this output voltage is RL, voltage across this RL, load resistance we can write, current passing through the load resistance is I, and it is RL. Assume that it is equation number 2. Now we'll substitute equation number 1 in equation number 2. Now if you substitute equation number 1 and 2, in place of I we have to substitute this one. Okay, V naught is equal to, in place of I we have to substitute Vi minus V gamma divided by Rf plus RL into RL. Okay, we know that in ideal diode, okay, in ideal diode, V gamma and Rf both will become 0. If you substitute here, we will get V naught is equal to Vi divided by RL. Here V gamma is equal to 0 and Rf is equal to 0 and RL. Okay, RL get cancelled. Finally, we will get V naught is equal to Vi. V naught is equal to Vi here. So output is exactly equal to the input if we give the positive half cycle to the rectifier circuit. Okay, we are not applying the KVL in the loop 2 because here loop 2 the current is equal to 0. As it is an open circuit, the current is 0. That's why we are applying the KVL only in the loop 1. Okay, so we are getting, if we give the positive half cycle to the rectifier circuit, we are getting output is exactly equal to the input. For the positive half cycle of the input AC, the output waveform is V naught is equal to VA. That is, output is exactly equal to the input. So this is the input and it is the output. Okay, input we are giving AC. It is 0 and it is pi. It is a 2 pi. It is a 3 pi, 4 pi and 5 pi. 4 pi and it is 5 pi with respect to omega t. Okay, time period is with respect to omega t. I assume that it is the input voltage Vi and it is the output voltage is V naught. Okay, here also cycle 0, pi, 2 pi, 3 pi, 4 pi and 5 pi with respect to omega t here. Here positive half cycle, we are giving only positive half cycle to the rectifier circuit. If we give the positive half cycle, we are getting output is exactly equal to the input here. Output is exactly equal to the input. Okay, here also here this is also positive half cycle. For the positive half cycle, okay, the output is exactly equal to the input only. Input is like this. This is input here. The output is exactly equal to the input because output is equal to the input for the positive half cycle. Here also output is exactly equal to the input for the positive half cycle. Okay, so this is about the in the center tapped full wave rectifier. If we give the positive half cycle to the rectifier circuit, these are the outputs we will get. Now if we give the negative half cycle, what will happen? We'll see. For the negative half cycle, this is a positive and the negative. Out of this positive and negative, we are giving the negative half cycle to the rectifier circuit. If we give the negative half cycle, okay, what will happen? We'll see here. This is the input AC. Input is AC. Okay, there are two diodes we are using. And it is a diode D1 and it is a diode D2. As it is a center tapped full wave rectifier, we are taking that load resistance tapping at the center of the transformer here. Okay, it is a negative terminal. It is a positive terminal and it is called as RL. Sorry, here we will take RL at outside. Okay, it is RL and it is a V naught. Voltage we will measure across this load resistance. Okay, here also that, but here we have to take the terminals are reversed here. negative terminal, positive terminal, because the cycle is reversing here. It is a negative half cycle. That's when it is a negative terminal. Terminals will be reversed. This is only the key point. Minus and plus, from the positive to negative. This we have to take the negative and positive here. Before positive and negative, now as the cycle is changing, negative and positive, it is the input voltage is VI. Here also it is a negative and it is a positive. It is the input voltage is VI. It is a P type of the diode and it is a N type of the diode D1. It is a P type and N type. So now we'll see which terminal is connected to which. We'll see. Negative terminal of the supply is connected to P of D1. Next, positive terminal of the input is connected to N of D1. Positive terminal is connected to N of D1. Okay, now in the downside, positive terminal of the input is connected to P type. Positive terminal of the input is connected to P of D2. Next, negative terminal of the input is connected to N of D2. N of D2. See here, N is connected to, negative is connected to N of D2. Okay, so if we observe the terminals clearly, negative is connected to P and the positive is connected to N. Then we can say that diode will be in reverse bias condition. Here, positive is connected to P and the negative is connected to N. Here, diode D2 will be in the forward bias condition. So for the negative half cycle, diode D1 is for reverse bias and the diode D2 is in forward bias. Okay, now we'll see the resultant circuit is. Here, this is a negative half cycle. When the diode is in reverse bias condition, it is replaced with the open switch here. As the diode D1 is reverse bias, we are replacing with the open switch. It is a load resistance RL. As the diode D2 will be in the forward bias, the diode will be replaced by cut-in voltage that is connected in series with the forward resistance RF. Okay, so this is the resultant circuit of the negative half cycle. Okay, now we'll see what are the equations, output equations we will get. The negative half cycle, this is the negative of the cycle. It is input is, okay, here it is the input is AC. Input is AC, input supply is AC, that is 230 volts we are giving. Okay, as the terminals are reversed here, the negative and the positive. The negative terminal and it is a positive terminal, it is the input voltage is VI. Okay, it is the load resistance, negative, positive. Output we will measure across the load resistance. It is a V gamma R and RF, forward resistance. Negative terminal and it is a positive terminal. It is the input voltage is VI. Okay, now here we will take the terminals downside. Okay, then we can take the loop clearly. It is V gamma and it is RF. Okay, so this is a negative terminal, positive terminal, negative and positive. As the cycle is reversing here, now apply KVL in the down loop, because in the upper loop the circuit is open. As the circuit is open, the current is 0. That's why we are applying the KVL in the loop to here, down loop. Okay, if we apply KVL here, if we apply KVL at the down loop, we will get +2 minus VI, +2 minus VI, -2 plus, sorry, we will take the first two voltages here, -2 plus V gamma is equal to voltage drops are I into RL plus I into RF plus I into RF. See here, +2 minus VI, -2 plus V gamma is equal to voltage drops are I into RL plus I into RF. Now take I is separately, we will get -VI plus V gamma divided by RL plus RF. Assume that it is equation number 1. Okay, now voltage across RL V0 is equal to I into RL. This is equation number 2. The next step is substitute equation number 1 in equation number 2. So in place of I, we have to substitute this equation where we will get V0 is equal to minus Vi plus V gamma divided by RL plus RF into RL. We know that since for the ideal diode, V gamma and RF both are 0. Substitute this here. Substitute in this equation, we will get V0 is equal to minus Vi. V gamma is 0 and divided by RL into RL. Okay, in the center tap to full wave rectifier, we will get output is equal to RL get cancelled. V0 is equal to minus Vi. We will get in the negative half cycle. If you give the negative half cycle to the rectifier circuit, center tap to full wave rectifier, V0 we will get V0 is equal to minus Vi. Okay, this is about the negative half cycle equation. Now, if you see the waveforms for the negative half cycle of the input AC, the output waveform is for the V0 is equal to minus Vi equation. Okay, output is for the negative half cycle. It is a positive half cycle. It is a negative half cycle. It is a positive and the negative. It is a positive. If you give the negative half cycle, the output is, this is the output V0. Okay, and it is input is Vi. Okay, output is exactly equal to the input, but in opposite direction here. Okay, here output is exactly equal to the input. V0 is equal to the Vi, but in opposite direction, minus Vi. Opposite direction means we will get the upside here. Okay, V0 is equal to Vi, but in opposite direction, we will get the waveform at the upside here. Okay, so this is about the, if we give the negative half cycle to the rectifier circuit, we will get the output waveforms like this. Now, if we combine both the positive and the negative half cycles, here, this is assume that it is the input voltage Vi. Okay, it is a omega t. Okay, it is also with respect to omega t. Okay, it is the output waveform is V0. It is 0. It is pi. It is 2 pi. It is 3 pi. And it is 4 pi. Okay, now here also it is 0, pi, 2 pi, 3 pi, and 4 pi. For the positive half cycle, we got V0 is equal to Vi. That's why in the positive half cycle, diode D1 is in on condition, but the diode D2 is in off condition. But we got in the negative half cycle, the output is exactly equal to the input, but in opposite direction. V0 is equal to minus Vi. That's why here D2 is equal to on condition in the negative half cycle, but D1 is off. Here, if you see the positive half cycle and the negative half cycle, in the positive half cycle, the same. In the positive half cycle, D1 is on, but D2 is off. In the negative half cycle, if you see in the negative half cycle, but here D2 is in on condition, but V0 is equal to Va, but in opposite direction. D1 is off. Okay, as the two cycles, positive half cycle, negative half cycles, two cycles are processing to the output. That's why it is called as full wave rectifier. Okay, here V0 is equal to Vi, and here V0 is equal to minus Vi. That's why we are getting two cycles, we are getting upside only. So this is called as a pulsating DC of the center tapped full wave rectifier. So these are the two cycles are conducting here. Positive half cycle as well as negative half cycle. Two cycles, positive and negative, are processing to the output. As this is, you have to remember here, this output is exactly equal to the input here. Output is exactly equal to the input. But why we are getting upside? Because V0 is equal to minus Va. That's why we will get the waveform at the upside. Okay. So now let's calculate all the parameters of the center tapped full wave rectifier. If you see the waveform, so both the cycles, positive and negative half cycles, are conducting. Both the cycles we are generating in the output. Okay, if you see the time period, okay, time period is pi here. If you see the area of conduction, okay, for the time period is pi, total 0 to pi is conducting. That's why area of conduction is 0 to pi. If you see the average value formula is area of conduction divided by time period. Area we will find out by using the integration. Okay, V average is equal to 0 to pi. The area of conduction is from 0 to pi. And which waveform it is? It is a voltage waveform. With respect to omega t we are doing, that's why d omega t. Time period is pi. Denominator we will get the pi here. Okay, this V we will replace it with Vm sin omega t here. Since instantaneous value formula is V is equal to Vm sin omega t, instantaneous value formula. Okay, we replace V by Vm sin omega t with respect to d omega t divided by pi here. Now we'll see. I'm separating Vm by pi here. Vm by pi 0 to pi sin omega t d omega t. I'm taking Vm by pi separately. Here, if you see the integration of sin omega t is integration of, since we know that integration of sin omega t is equal to minus cos omega t. So integration of sin omega t is minus cos omega t, but here the limits are 0 to pi. So if you apply the limit, upper limit minus lower limit. Upper limit is cos pi minus lower limit is 0. Since cos pi is equal to minus 1 and cos 0 is equal to 1. So now we will replace cos pi by minus 1 and cos 0 by 1. Minus 1, minus 1, minus 2, minus 2 into minus plus 2. Okay, we will get finally V average is equal to 2 Vm by pi. Here we will get Vm by pi minus of minus 2. We will get here minus of minus plus 2 Vm by pi. So finally V average value of the center tapped full wave rectifier is 2 Vm by pi. Now we'll see the RMS value. Okay, so this is the average value we got. Okay, for the RMS value means what? Root mean square. For this mean value we have to take the root as well as the square here. I am taking the root for this and I am taking the square. Vm square sin square, Vm square sin square omega t. Simple. You have to remember this mean value, and for that we have to take the square as well as the root. It will become root mean square. Now to simplify the above root, I am taking sin square omega t is equal to 1 minus cos 2 omega t. Since sin square omega t formula is equal to 1 minus cos 2 omega t divided by 2. This is the formula we are having. So I am replacing this sin square omega t by 1 minus cos 2 omega t by 2. Now I am taking the term separately. Vm square by pi here. I am taking 1 by 2 integration 0 to pi 1 by 2 omega t and 1 by 2 cos 2 omega t. These two terms I am taking separately. Okay, integration. Okay, yeah. For the integration 0 to pi we are having 1 by 2, and for the integration 0 to pi 1 by 2 we are having. For the both the terms 1 by 2 is the common. That's why I am taking 1 by 2 is common. That's why Vm square by 2 pi. Okay, taking separately 0 to pi d omega t minus 0 to pi cos 2 omega t. As we know that integration of d omega t is omega t, and the integration of cos 2 omega t is sin 2 omega t by 2. Okay, the limits are 0 to pi, here also 0 to pi. Since integration of cos 2 omega t is equal to sin 2 omega t divided by 2. Okay, now we'll apply the limits here. Vm square by 2 pi, upper limit is pi, lower limit is 0. And here minus sin 2 omega t by 2, upper limit is 2 pi and the lower limit is 0 by 2. So we know that sin 2 pi is equal to 0 and sin 0 is equal to 0. Since we know that sin 2 pi is equal to 0 and sin 0 is equal to 0. Okay, I am substituting these values here. Here we will get Vm square by 2 pi into pi minus 0. As a numerator 0 minus 0, total term will become 0. Here pi get cancelled, Vm square by 2 here. Okay, So square root cancel, finally Vm by 2. So VRMS value of the center tapped full wave rectifier is Vm by root 2 we will get finally. Here we'll see the form factor value. Form factor is VRMS by V average value. Form factor VRMS value of the full wave rectifier is Vm by root 2 and the average value is 2 Vm by pi. We will get 1.11. So form factor of center tapped full wave rectifier is 1.11. So peak factor formula is peak value by RMS value. So peak value is Vm and RMS value is Vm by root 2. Finally Vm get cancelled here. Vm get cancelled. Here also Vm get cancelled. We will get root 2. Okay, peak factor of center tapped full wave rectifier is root 2. Next we'll discuss about the ripple factor here. Okay, now we'll discuss ripple factor. So ripple factor is defined as the ratio of RMS value of the AC component to the DC component. The ripple factor functionality is to explain the how much amount of the AC ripples present along with the DC output. Okay, the output we are getting, that is pulsating DC, not the pure DC. In that pulsating DC, we have the ripples. Okay, how much amount of ripples present in the output of the DC, that we will find out by using this ripple factor. The ripple factor is indicated with the gamma. Okay, now let's see. Gamma is equal to, the formula is VAC by VDC. Okay, AC component to the DC component here. Okay, VAC we will represent it in under root of VRMS square minus V average square here. So if you see the gamma is equal to under root of VRMS square minus V average square, wherever VDC is we will represent it in V average. Okay, this formula we will substituting in the above. Okay, now if we take the V average to the inside, we will get V average square minus V average whole square divided by V average whole square here. Okay, now I am taking separately here under root of the gamma is equal to under root of here under root we will get under root of VRMS whole square divided by V average whole square, V square RMS V average whole square minus VRMS whole square divided by V average whole square minus V average whole square by V average whole square, we will get 1. Both are get cancelled. Finally, we will get VRMS by V average, VRMS square by V average square minus 1. Now, we know the formulas. VRMS value of the full wave rectifier is Vm by root 2. That is whole square divided by VRMS value of the full wave rectifier is 2Vm by pi. This is also whole square minus 1. Here Vm square get cancelled. Okay, here we will get under root of we will get pi square divided by we will get here root 2 get cancelled. Square root cancel, we will get 2 into 2 square means 4. Okay, 2 into 4 minus 1. Okay, ripple factor, if we calculate this above value, ripple factor of full wave rectifier, we will get 0.48. This is the ripple factor of the center tapped full wave rectifier. Now let's see efficiency. Efficiency is the ratio of output DC power to the output AC power. Sorry, input AC power. The ripple factor is indicated by in eta here. Okay, efficiency is equal to output power by input power into 100. Okay, output is DC and input is AC. PDC divided by PAC. Power DC divided by power AC into 100. Okay, DC, the formula for power DC is I square average into I average whole square into RL. The power in AC formula is okay RMS square into RL. Okay, IRMS square into RL. This is the formula for the efficiency. Now, if you substitute these two PAC and PDC in the eta, we will get I average square into RL divided by IRMS square into RL. Okay, now if we calculate here, RL get cancelled. We know that I average value is Im by 2Im by pi, 2Im by pi whole square divided by RMS value is Im by root 2. Im by root 2 whole square into 100 here. Here Im square both are cancelled. Finally we will get 4 divided by pi square into 2 here. Root square cancel into 100. Okay, eta we will get, if we calculate the above value, we will get 81%. Okay, this is the efficiency we will get in the center tapped full wave rectifier. Now let's see transformer utilization factor. Okay, how much amount of DC or how much amount of transformer we are using to convert into AC to DC, transformer winding we are using to AC to DC. This we will tell by using the transformer utilization factor. Okay, transformer utilization factor is a ratio of power DC divided by power AC of secondary winding of the transformer. Okay, here power DC is I average square into RL, but power in AC, the input the transformer secondary winding, we will take the power formula is IRMS into VRMS. Power is equal to V into I. Okay, we don't take RL here because we are calculating the power at the secondary winding of the transformer. At the secondary winding there is no RL term, so that's why we have to use this. Okay, now if we calculate the value, I average value, we know that 2Im by pi whole square into RL divided by IRMS value is Im by root 2 and VRMS value is Vm by root 2 into 100. Okay, now here if we calculate this equation, we will get here Im square and the Im both are get cancelled, and we will see what is the remaining equation. We will get 2 into Im divided by pi into RL divided by Vm divided by root 2 into root 2, we will get 2 into 100 we will get here. So I am writing here Vm, since we know that according to Ohm's law V is equal to I into R. Vm is equal to, I am writing Im into RL. Okay, if we write like that, we will get 2 into Im divided by pi into RL divided by Vm is equal to Im into RL. Im into RL divided by 2 into 100. Here Im get cancelled and the RL get cancelled. Finally we will get, if we calculate the above equation, transformer utilization factor is equal to 4 divided by pi into 100. Here we have done one small mistake here, that is here it is 2 square here, that's why here it is 2 square, here also 2 square. So here 4 into 2 square is 4 into it is 2. Okay, and it is also here it is pi square under root, that is pi square. So if we calculate the transformer utilization factor, we will get 81% here. Okay, this is about the transformer utilization factor. Now let's see peak inverse voltage. Okay, so this is the maximum value of the reverse voltage which the rectifier has to withstand during the non-conduction period. Okay, so if we take positive half cycle here, this is a positive half cycle. In the positive half cycle, in the reverse bias, the diode D2 will be in the reverse bias. When the diode will be in the reverse bias, we have to calculate the what is the maximum reverse voltage across this diode. The voltage across this reverse bias diode is nothing but the peak inverse voltage. Okay, yeah. We are taking the positive half cycle here. Input AC. Input is AC. It is a positive terminal and it is a negative terminal. It is a positive and negative. It is a VI. It is V gamma and it is a forward resistance VA. It is a negative, positive. Okay, and it is the output voltage is V0 and it is a RF. Sorry, RL it is. RL is a forward resistance. Okay, RL is a load resistance and it is a plus minus. It is a input voltage is VI. Okay, now we have to take the it is a positive terminal and it is a negative terminal. It is VD. Now apply KVL here. Assume that it is I current is flowing. We apply KVL in the down loop because here the diode is in open circuit in the down loop only. Apply KVL. We will get -2 plus VD, -2 plus VA, -2 plus V0 is equal to 0. Okay, here diode voltage VD is equal to, we will take here 2 VI and V0 right side here. We know that, since we know that V0 is equal to output voltage is equal to input voltage, that's why VD is equal to minus VI, and in place of VI we have to V0 we have to substitute VI. VD is equal to minus 2 VI. Okay, so we know that instantaneous value formula V2 is equal to VI is equal to Vm sin omega t. Okay, VI we know that instantaneous value, since Vm sin omega t. Here this negative value indicates the inverse value and this 2Vm indicates the peak value. So from this we can say that peak inverse voltage of the center tapped full wave rectifier is 2Vm. Center tapped full wave rectifier peak inverse voltage is 2Vm. Negative value indicates the inverse voltage and a 2Vm indicates the peak voltage. Peak inverse voltage is 2Vm. Okay, now if we see the summary, so this is V average we got 2Vm by pi, and VRMS value we got Vm by √2, and form factor is equal to 1.11, and the peak factor is equal to √2 we got, and the ripple factor we got 0.48, and the peak inverse voltage we got 2Vm, and the efficiency we got 81%, and the transformer utilization factor is also 81% we got. Okay, out of all the parameters, okay, except this peak inverse voltage, remaining all are the advantages only. If you see here, ripple factor is 0.48. This is also advantage. The ripples are less compared to the half wave rectifier, and the efficiency is 81%. That is also advantage. Transformer utilization factor is also 81%. But the peak inverse voltage generally it should be Vm, but here we are getting double 2 Vm. Okay, so because of this reason we don't use the center tap full wave rectifier. So that's why in the next class we will discuss about the bridge rectifier. In the bridge rectifier we will see whether these disadvantages will be rectified or not, we will see. Okay, so because of this reason we are going for the next rectifier, that is bridge rectifier. These are all our advantages only except peak inverse voltage. Okay, so in the next class we will discuss about the bridge rectifier, whether we will get the good peak inverse voltage or not, we will see. Okay, thank you.